Hi everyone. Last time we looked at the derivatives of the inverse trigonometric functions, inverse of sine, inverse of cosine and inverse of tan, and they were the rules that we developed. So the next obvious step, instead of derivatives, is integrals. And it really is quite straightforward. We say, of course, that the integral of 1 over 1 minus x squared with a radical sign under there would equal the inverse sine of x plus a constant. Just like we do for anything where we've taken a derivative, we can reverse the process with integration. The next one, integral of negative 1 over 1 minus x squared, would be the inverse, oops, writing the wrong thing, it would be the inverse cosine of x plus our constant, and the integral of 1 over 1 plus x squared. Oh, did I forget to write dx's as well? Well, I'll quickly fix that. It's getting too excited here, getting ahead of myself, so I'll just put the dx on the top. 1 times dx, or negative 1 times dx, really means the same. So what did we get? This one would be the inverse tan of x plus our constant of integration. Now, that's the lesson. There's your rules. Of course, nothing's ever quite as straightforward as that, is it? Because you are going to get questions which are not just 1 minus x squared. There'll be other constants and other things in there. So perhaps we could take a straightforward example first of all. So let's imagine in our first example here that we were asked to find the integral of 1 over 1 minus 9x squared, and we put a radical sign over that. Don't forget my dx this time. So that's almost the same as the first rule, but we have this annoying number 9 sitting here in front of our x squared. We have to deal with that somehow. It would be ideal if I could write this in the form using a different variable, 1 minus u squared, because then it's perfectly in the right shape. So I'd better make a substitution then. What would u need to be so that u squared was 9x squared? I think we can see that we would have to let u equal 3x, and I can't put dx on the second line. I will need to find what du equals. So du dx would equal 3. Du over 3 would equal dx. That's nice. I'll put du over 3. So my constant of 1 over 3 could come to the front, and then I have the integral exactly as I need it. 1 over the square root of 1 minus u squared du, and that is exactly what we had in our formula, using letter u instead of letter x, but it's the same result. We will end up with the inverse sine of u plus our constant. So writing this in terms of the original variable, u equaled 3x. I didn't forget my third, I'll just put over 3 plus c. So there's a reasonably nice little example of how we can still use our substitution technique and combine that with our new formulae we've got here for these ones. Now, there's a couple of other things that might happen as well. For instance, what if we had something like the integral of, now I might just go symbolically here, what if we had not 1, but we had some other square number, minus x squared dx. Now that's a bit annoying. Our formula said we have to have a 1 here minus x squared, not some other number. So what am I going to do to make it look like I need it to look? Well, I think I know what I'll do. I will leave this alone. I will consider this to be a squared outside 1 minus x squared over a squared. Oh no, I forgot my radical sign, didn't I? Let me just embellish this slightly. There's my radical sign, and it's 1 divided by all of that stuff. I've got a tiny vinculum in there. I hope you forgive me. So what have I done? I've taken a common factor of a squared from itself to leave the 1. That's what I needed. I needed my formula to have a 1 there. Subtracting, and now I have to have divide by a squared. It seems like I've just transferred the problem to somewhere else. Well, we'll follow along with this story and see where we go. I could have this as the root of a squared by the root of 1 minus. Now, what if I don't call that x squared over a squared? What if I call it x over a all squared? Now it's looking a bit more like 1 minus something squared. That vinculum still belongs there. Now what would be the square root of a squared? Well, that's just a. And having that in the denominator, I could bring my constant of 1 over a to the front. That was where the square root of a squared ended up. Now this, it's still not looking wonderful. I would really, really like that to be 1 minus a single pronumeral squared. Well, this is where my substitution technique comes in. I will let u equal x over a. And I need to, of course, find what dx is the same as to substitute. So du over dx would equal 1 over a. A multiplied by du equals dx. There's my replacement, a multiplied by du. Now, isn't that a happy accident? Look at that. The constant 1 over a at the front cancels with the letter a that was introduced with the infinitesimal. So I've literally got the integral of 1 over the square root of 1 minus u squared du. That is exactly the rule. This will be the inverse sine of u plus c. Now, I'll write it on the final step. Instead of u, remember u was x over a. Well, why did I put a at the end? Because it's a constant of integration at the end there. So when we had this a squared being a nuisance at the front here, ruining our lovely formula, it just turned out that we could still solve by having a little bit of a trickery here where we took a common factor of a squared, and because that was under the radical, it was really just 1 over a, and then the change of variable with substitution, and it all worked out reasonably well in the long run. Now we can do the same sort of process here if we start with, instead of a squared minus x squared, if we start with any of these forms we've got up here in the yellow box, we can use the same type of trick. I don't want to demonstrate all 3 of them, of course. I want you to have some practice at doing this yourself. But the point I want to make is that any of our inverse trig derivatives can be written the other way around as integrals. Yes, that's something we already knew. We can write integral notation as the sort of opposite process to derivative notation. And our substitution technique, which we've been practicing for a little while now, still comes in very handy to get us out of strife. And remember, if we've got something that looks almost but not quite the same as what we have in our rules here, we'll usually be able to find a substitution to get us having a rule like the one I'm showing now that looks the way we need it to look. And this is another common factor one. A common factor is another thing that we will often need to do to get our rule looking, that was my goal, to get the rule looking like the form that we have up the top of the page. Oh, I think that's enough for now. Have a try at the exercises yourself in the textbook, and don't forget, if you have any questions, you can always send me a message via Teams. Thanks for watching.